chat or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question, however, that you'd like to ask our guest speakers, please type that into the Q&A. Otherwise, they're really easy to lose. It'll help us keep track and know whether or not we've answered your questions. So without further ado, welcome. April is officially Citizen Science Month, and we are thrilled to have a guest host tonight.
For kids, that involves the Disney Channel, National Geographic, PBS. It's a really fun one. You'll find it at citizensciencemonth.org. So this is what you might find if you come to SciStarter. It's a place to find thousands of projects that we've organized from all over the internet and made them searchable. So you can find projects that are related to astronomy. You can find projects that require a telescope, projects you can do near you, events, and so forth. And probably most of you know what citizen science is, but just in case you don't, I don't want to make assumptions here. It's typically a collaboration between scientists, like those that you'll hear from in a couple of minutes, who need help from the public, the rest of us. And so we like to say that if you're curious or you're concerned about an issue and you're motivated to do something about it, you will absolutely find a way to do that through citizen science. The idea is that you're helping to collect or analyze data that somebody makes use of. So it's not just an opportunity for you to learn, although you will, you're actually actively involved in important research projects. We're encouraging you tonight to go to scistarter.org/astronomy mag, short for magazine, and you'll see an opportunity to sign up for SciStarter. Everything is free. We want you to sign up so that you can continue to find projects, but also so that you can track your contributions across projects, across websites and applications. And before I toss it back over to Vivian, this is also what you'll find on Astronomy Mag, on scistarter.org/astronomy mag. The 3 projects that we're going to feature here today. And when you click on either of those projects or all of those projects, you'll find step-by-step instructions, videos from the project scientists, and just more ways to understand how to get involved in these projects. On that page 2, you'll see an invitation to register to learn more about an event that we're doing next month. It's the first ever NASA CitSciCon. That's short for Citizen Science Con, I guess conference. It's a 2-day event, open, and it's free. And we'll have an ongoing series of open door events where you can jump in, learn all about the NASA citizen science projects that are there, hear from the project leaders, and learn how to just get involved and make a difference. Thank you, Vivian. Well, that's what it looks like. Thank you, Caroline, for putting this slide in here. It looks amazing. Thank you.
That's fabulous. Thank you all so much. Great. Thanks, Caroline. Thanks, Darlene. And I'm just going to hand it over to Dave Eicher.
Well, thank you. Excuse me. Thank you very much, Vivian, and thank you, Darlene, and everyone for having me here. It's a great joy, a great pleasure to be here with you and everyone who's here, who's made this event happen. It's the NASA Night Sky Network. It's Astronomy Magazine. It's SciStarter. We have 3 very exciting citizen science projects, and we're going to hear about tonight, and leaders. And this is not just any old citizen science. This is citizen science in a golden age of astronomy, because as many of you undoubtedly know, we are in the greatest era ever in terms of the pace and the numbers of amazing discoveries and exploration that is going on. And it used to be, years ago, a generation ago, people talked about, citizens are going to help scientists out with their work and research. And, it maybe wasn't quite exactly, well, now you really can. You can do real science and in a very legitimate way contribute to our understanding of what's going on. This is tremendously exciting, and it's an honor to be a part of this. And just to talk just for 1 second about how we're going to do this, we're going to, don't be frustrated with the question. And I know people are going to have a lot of questions and answers, and this is fascinating experts here with us tonight. We're going to have 1 question between each of the presentations, but then we're going to do a lot of questions if we can at the end. So we'll do 1 question between each of the speakers, but don't be upset if your question doesn't go right away, because we hope to have a lot of Q&A time toward the end of this great event. So again, without further ado, I'm the editor of Astronomy Magazine. Thank you, Vivian, for mentioning that. Astronomy, you can find out what we're doing at astronomy.com if you'd like. We're very pleased and happy to be a part of this group in a way. And without further ado, I would like to introduce our first speaker, who has maybe the coolest citizen science name for her project ever, Aurorasaurus. Dr. Liz McDonald. She works for NASA at the Goddard Space Flight Center in Maryland, and she leads the Aurorasaurus Citizen Science Project, which uses citizen science and social media to predict northern and southern lights, aurorae. In 2018, Liz announced the discovery of a new type of aurora called STEVE, an acronym for Strong Thermal Emission Velocity Enhancement. You can report on whether or not you see aurorae at her website event site, which she will undoubtedly tell you about. And Liz is going to give us a full explanation, I think, now of this very exciting project.
All right, thank you so much. Let me share my screen and share the sound. So I have a video with sound. Nope, can't share the sound. Is it sharing the screen?
Looks great.
Okay. And it's the correct way?
Perfect.
Okay, great. Well, it's an honor to be here and to talk to all of you about the Aurorasaurus Citizen Science Project. And Steve, as just a preview, is shown in this very beautiful photo by Paolo Fedosi over the Alberta area. And I will talk much more about that. I want to acknowledge our funders and partners and all of the citizen scientists who contribute, especially the Alberta Aurora Chasers, and really celebrate citizen scientists here in the month. So next, I just wanted to give on the right-hand side here the link to our project. You can also tweet us and tell us if you've seen Aurora, and we actually can pick that up and put it on our map. We started this project not knowing fully what we were getting into and how kind of disruptive it is and how innovative the results might be. But you know, we were facing a dearth of data, and there's also, it's extremely hard to tell you exactly when the aurora will be visible over Bellevue. And, you know, that leads to a lot of people not being as successful as they could be. But almost 10 years ago, we realized that with social media and smartphones, we could start to create a platform for alerting people in near real time that other people near them were reporting aurora. So it kind of works like an eBird in space, and also reaches out to new audiences and really increases the numbers of people that can see aurora. So this is one super busy slide about our project, which has all these different aspects. But you can see some of the beautiful citizen science submitted photos in the little GIF here. And we've had a number of reports, millions of tweets that we've looked at, a lot of papers. If you look at the website, it will be displaying the map of where the aurora should be visible overhead, as well as where people are reporting aurora or potentially tweeting about aurora. And then you can contribute there, as well as if you're somewhere that can't even see aurora, you can still look at the tweets and help us upvote them and find really the real-time tweets. So that has been going on since the last solar maximum, when the sun was really active. The sun has not been that active in recent years, but it's starting to pick back up. And we are also revamping our website for newer technologies as well. So you will be seeing that soon. So talking a little bit about Steve and how the photos have really helped our citizen science project grow. You know, here's one beautiful example of Steve from Manitoba, actually, by Krista Trinder. And, these pictures just pop. They just, people are riveted by them. They want to tell they want to know the story. They want to know what the heck this is. And it's actually also has a scientific benefit that we're starting to, especially for aurora, which are caused by the precipitation of particles from space into the upper atmosphere and how that releases light. As our cameras get better and better, and commercial cameras are now as good as the scientific grade cameras were a few decades ago, we can see more photons. And so we can see the visible manifestations of the upper atmosphere and the near Earth magnetic space environment in a way that we never could before. And that's actually led us to discover something that was overlooked, and that's Steve. Which is shown here in a little cartoon version, kind of as a very narrow east-west aligned ribbon that cuts across Canada and the US, the northern US in this case, while the aurora is far to the north. And so it's really this sub-auroral phenomena that's been quite overlooked. And the discovery isn't the photos themselves, because actually people have been photographing it for a number of years. The discovery was really the meaning and the understanding of what Steve is, which happened after we combined the photos from citizen scientists all over, especially in Alberta and Saskatchewan and Manitoba, with traditional scientific grade cameras fielded by the University of Calgary that are also all over Canada. And combine that as well with the European Space Agency's satellite called SWARM. And it was seeing the particles that actually cause the aurora. Are you guys hearing the sound now?
The aurora, and they started noticing something that was overhead as well when they were seeing the aurora far to the northern regions. It was unlike most aurora. Talked to the scientists, we didn't know what it was. And together they said, we'll keep taking observations and we'll call it Steve in the meantime. Steve is mostly a very narrow purple arc, and sometimes it has these little green features that go along with it as well that are kind of like waving fingers or a picket fence. That means that there's plasma physics happening up there to cause that light and to make these little discrete features that we don't understand yet. We now have some satellite observations from the ESA satellite called SWARM that show that Steve optically is associated with a very strong flow in the particles in the ionosphere, the upper level of our atmosphere. Steve is important for a number of reasons. It's really exciting that people armed with cameras all over the globe can capture something that we didn't fully understand and shed new light on that. It's also really exciting that this happens further to the south where there are more people. So it might be a kind of aurora that more people can see than the usual kind. We're now able to look up at the sky and see things about the aurora and this sub-auroral region that we never understood before. And then we can correlate that with our traditional observations and lead to greater understanding.
Sorry for repeating myself. I didn't think the sound in the video was going to work, but it's much better, the edited version of me with the pictures in the background as well. So yes, and so Steve has really grown and gone viral across the world, which has really been very engaging and contributed to greater understanding of the process of doing science and how, it was teamwork and how we all listen to each other in order to, not dismiss this as something, just another type of normal aurora. But it's also been translated into many different languages, and the story's been told at many different levels. And one of my favorite is the Wow in the World podcast for kids. It's so fun. It's such a fun version of Steve, and they really highlight the science also. So, and the way that science works. And of course, the aurora is not just a scientific phenomena, it's also really important to people's lives and well-being, and it's like an addiction to chase it. And so we want to help people do that safely and increase access and increase understanding. And so we're doing that with a variety of different projects. And you can definitely check out our blog for more information about our project, blog.aurorasaurus.org. And you can also even follow Phenomenal Steve on Twitter. And this is not me, this is run by a citizen scientist, and just has a great personality as well. So that's it. Thank you so much. If you want me to nerd out more on Steve, I do have one, more depth backup slide on that.
That's fantastic, Liz. Thank you very much for that. And I believe that Vivian is going to sort a question. Am I correct, Vivian, on that? Oh dear.
We have actually lost Vivian temporarily, and so I'm trying to sort out what we've got here while you all were talking. So
okay. Oh no. Uh-oh, poor Vivian. We need to retrieve Vivian.
Okay, we do have one question here, and so why don't we go ahead and so Vincent asked, what are the new discoveries happening now related to Steve and citizen scientists?
Oh, that's a great question. Thank you, Vincent, who is probably the same Vincent who's a phenomenal undergraduate student with his own Aurora camera in North Dakota called NODAC. But some of the new discoveries about Steve, most recently in January, we actually published a paper on some of the picket fence features, and not just the discrete picket fence that you see kind of like fingers, but also there's even tinier sub-elements of that look like, they kind of look like a point source of Aurora that gets smeared out in the camera's image. And those are like also completely crazy little features that are not consistent with particle precipitation and the traditional version of how Aurora is formed. So using citizen scientist images and triangulating on the height of these new features. That was also done with photographers, but also a citizen scientist himself, Michael Hunnekel from Germany, actually did the analysis of the triangulation and has made his own catalog of a whole bunch of Steve events as well as sub features. And he's one of the ones who noticed these tiny features, as well as the lead author, who's Professor Josh Semeter from Boston University. So we can put the link to that paper or press release in the chat as well. Thanks.
Fantastic. Thank you, Liz. That is really terrific and very interesting and groundbreaking, of course, too. Congratulations on that. And now we're going to go on to Dr. Patrick Treighthart, who I have seen before. Good to see you again, Patrick.
You too.
And you're going to tell us about a spiral graph.
Yes.
Another exciting project. And Patrick is an astrophysicist whose research is focused on the morphology of disk galaxies, and also takes part in public outreach activities that increase access to astronomy, science in general. One of these projects is Spiral Graph, which we'll hear about tonight, in which you can help scientists measure the curvature of spiral arms in galaxies by participating in the Spiral Graph program, which is part of Zooniverse, and I presume you'll give a website URL as well.
Yes, I'll do that at the end. Yeah.
Excellent. Take it away, Patrick, if you would.
All right. Let me share my screen. Okay. Yeah. So thanks for inviting me. I'm an astronomer at the North Carolina Museum of Natural Sciences, and as was mentioned, I'm interested in spiral galaxies. So let me give you a little bit of background as to what this project's about, and then how it actually works, and what we can learn from it. So spiral galaxies make up most of the galaxies that we see in the nearby universe, And so this little diagram here is Hubble classification diagram of galaxies. You can see the spirals here on the right side of this tuning fork diagram. And you can see that there are two main types of spiral galaxies. There are so-called barred spiral galaxies and then non-barred spiral galaxies. And these non-barred spiral galaxies, they essentially have a bulge in the center and then the arms wrapped around the bulge of the galaxy. So you can see that more clearly here. So here's the bulge. You can see the spiral arms wrapping around that. And the barred spiral galaxies are similar, only they have a linear structure running through the bulge, and then the arms tend to come off the ends of that linear structure, and we call that the bar. And so, so these are the two main types of spiral galaxies. But one thing you'll also notice is that with spiral galaxies, the way that this classification system is broken down is that you can see here on the left side, the spiral arms are much more tightly wrapped than they are here on the right side. And so we can actually group galaxies into a classification scheme based on how tightly wrapped the arms are and how large the bulge is. So these SA type galaxies or the SBA type galaxies have a large bulge and very tightly wrapped arms, and these SC or SBC galaxies have smaller bulges and much more open arms. So if we pay attention to if we look at every single galaxy essentially in the universe, we see, including our own Milky Way, we see that every galaxy tends to have a supermassive black hole in its nucleus within that bulge. And these black holes, the reason why we call them supermassive is because they range from millions to billions of times the mass of the sun. And so this flickery animation, because my computer's a little low on RAM, these are animations kind of showing the stellar orbits around an unseen object in our own Milky Way, in the center of our own Milky Way. And these stars are orbiting around an object that's 4 million times the mass of the sun compressed into a very small volume. And so the only thing it can be is a supermassive black hole. And so this is how we know that there's a supermassive black hole in the center of our own galaxy. So when we look at other galaxies, so for instance, I'm sure everybody's seen this image of this radio image of the center of an elliptical galaxy that shows essentially the supermassive black hole in that galaxy. So every galaxy we looked at seems to have a supermassive black hole in the center, but it's really unclear as to how these things form. They're so massive and they appear so quickly in the formations of galaxies, in the evolution of galaxies, that it's really unclear how they could form so quickly and grow so rapidly. There are a couple of ideas as to how this can happen, in that you can have essentially just giant gas clouds that collapse directly into very massive black holes that then merge and form these supermassive black holes, and that can happen very quickly in the beginning of a galaxy. Or you could have stars, very massive stars that form very, very quickly, burn out very, very quickly, explode as supernovas, form stellar mass black holes, and then those merge together very quickly and form these seeds for supermassive black holes. It's really unclear what the formation mechanism is. But one of the keys may be trying to find a rare type of black hole called an intermediate mass black hole. So these supermassive black holes range from millions to billions of times the mass of the sun, and stellar mass black holes range from, let's say 10 to 1,000 times the mass of the sun. These intermediate mass black holes that we don't really see range from thousands to hundreds of thousands of times the mass of the sun. And really, there are almost none that we have found. There are maybe a dozen candidates and maybe 2 or 3 actually confirmed intermediate mass black holes. So one of the interesting things would be to try to find more of these intermediate mass black holes in galaxies and see what's different about these galaxies compared to essentially every other galaxy. And maybe that can help explain the evolution of normal galaxies so that they grow with these supermassive black holes. Whereas these galaxies with intermediate mass black holes, we can see what's different about them and maybe what stopped them from growing into supermassive black holes. So we can look at these outliers to kind of figure out what's going on normally. And one way we can do that is based on a paper that was published in 2017, or actually before that, in the early 2010s, And what was found was that there seems to be a relationship between how tightly wrapped the arms are in a galaxy and the mass of the supermassive black hole in the galaxy. So what we can do is essentially measure how tightly wrapped the arms are, and we can use this plot, essentially this cartoon plot, to kind of determine the mass of the black hole that way. And so this is a really quick, cheap way to estimate the mass of black holes in galaxies for a large number of galaxies. We can do this very, very quickly with a large number of galaxies. I mean, generally, the other way of measuring it is, again, looking at the scattering of stars by the black hole, which takes a lot of telescope time. You know, it's essentially hard to do. But just looking at images of galaxies, measuring how tightly wrapped the arms are, I mean, it's a very quick and easy way to do it. So when we look at this plot, when we look at most galaxies that we see in the universe, or that we've been able to measure this with, we see that most galaxies tend to lie within this blue oval over here. So out here, you know, tightly wrapped arms, essentially high mass black holes. But if we can look at enough galaxies, if we can measure this winding parameter and estimate the black hole mass for enough galaxies, maybe we can get a few sprinkled down here that could potentially have intermediate mass black holes. And so that was one of the reasons why we wanted to start this project, is because we thought that maybe we could find some intermediate mass black holes. But there are other parameters that this spiral arm winding matches with as well. So one of the issues is that when you just use like sky survey images of galaxies, they tend to be not very good. And so this is an example of one of these images. And so you can kind of get a sense that this is a spiral galaxy, but really the contrast between where the arms are and where the arms aren't is very, very low. There's very little difference between that. And so to do this in any kind of automated way is actually very, very difficult for a computer, because it can't trace out where the arms are compared to the gaps between the arms. But humans are very good at pattern recognition, and they can actually see, you can actually see kind of get a sense of where the arms are. So for instance, I can see the bulge right here, and I can get a sense that there's an arm wrapping something like this, whoops, right there. And so this is a little cartoon kind of that shows kind of the solution we came up with. So the idea was, what if we show people images of galaxies, have them just trace out where they think the spiral arms are, and just throw away the image and measure the tracings. And if we get enough people to look at every single, you know, each individual galaxy, we can come to some kind of agreement as to where the arms are, and then just measure where people agree, and come up with a measurement for the winding of the spiral arms. So we developed this project. We called it Spiralgraph. This is just what the home page looks like. And I'll show you a link in just a second. But the way the project works is we show you an image of a galaxy, and the images we have, they should all be spiral galaxies. But what we found in the very beginning is that actually they aren't all spiral galaxies. There's some of these galaxies have been misclassified as spirals. So what we do is we show people an image of a galaxy, and then we ask them, is this essentially a non-interacting spiral galaxy? So in that, is it structured and not merging? Or is it something else? Is it a smooth galaxy? Is it a merging galaxy? Is it otherwise somehow untraceable? And if the answer is B, then we ask you to trace out the spiral structure of the galaxy you observe. So just to give you an example, this is an example of a merging galaxy down here that was classified as a spiral by another group. And obviously it's very disorganized. It's not centered in the image. There's very little regular structure to it. So this really is a merging galaxy here. Whereas this one is clearly a well-defined spiral galaxy that doesn't seem to be interacting with anything else. So you can clearly see the spiral structure here. And so if you select B, then we just have you trace it out, which you can see in this GIF right here. And so what we've done, so we've been running this project for about a year, and we have only recently run out of data. And so we're now waiting to collect more data, waiting to have more images, unique images of spiral galaxies, so that way we can actually have people trace out more galaxies. But what our initial, so we had 2 batches of galaxies. Our first batch had about 6,000, and our second batch had about 14,000. And in each batch, we'd had people classify galaxies, each galaxy 15 times, and then trace them if they thought it was a traceable galaxy. And from our initial results we found here, out of the 6,000 galaxies, we found that about 2,300 of them had very good agreement that they were spiral galaxies. Here, there were about 4,000 galaxies that were marginal, but then there were clearly some over here where everybody agreed it was not a spiral galaxy. So there were about 51 galaxies that were clearly not spiral galaxies at all. But you can see that there were about 300 galaxies that everybody agreed this was a spiral galaxy. So this was our cutoff mark here. So we have about, out of our first batch of 6,000, we have about 2,300 really viable galaxies. Although we do have data for all these other ones as well. And so to give you an example of what people have done, this image here on the left is one of the galaxies we've shown volunteers. And you can see, again, you get a sense of where the spiral structure is. The difference between the arms and interarm regions isn't very high, but you can clearly see the spiral arms. And then over here on the right, this is the aggregate tracings from 15 volunteers of this galaxy. And the software we have can, if we plug the left image into our software, it has a harder time measuring the winding of the arms than if we plug in this right image over here. And we're able to get really good measurements of these spiral galaxies. So not only can we get, for instance, using this black hole spiral arm winding relationship, not only can we estimate the masses of black holes in the centers, but there are also other relationships we can get from this, just from measuring the winding of the spiral arms. We can get the mass of the stellar bulge in the center of the galaxy. We can get the maximum rotation velocity of the galaxy. And from the maximum rotation velocity, that also tells us something about the amount of dark matter that galaxy contains as well, which is also amazing. I mean, it's pretty amazing that we can get both information about the very center of the galaxy and then essentially the entire galaxy as a whole as well, just from measuring how tightly wrapped the arms are. So not only are we going to get a lot of information from these spiral tracings that people produce, but we can also use the tracings to create an AI program to hopefully map out the spiral arms in galaxies by just plugging in an image. And hopefully we won't need people to do this anymore at all. So we have enough data now that we think we could actually train up an AI to learn where the spiral arms are in an image and actually map them out for us. And so this is actually a project that we plan on doing in the future. Once we get all this data analyzed, we actually plan on trying to create this machine learning program to do this. So as promised, here at the end, we have the link. Basically, this URL will take you to the SciStarter page with a link to the Spiralgraph project website. But then also, if you follow us on social media, especially the Spiralgraph Twitter handle, you can stay tuned for updates. We can let you know when we have more data that we can have people trace and things like that. But we'll also be posting, results as we get them as well. So you can follow us on the web page for the project, or you can follow us on Twitter or Instagram as well. You can stay up to date with what's happening with the project.
Fantastic. Thank you, Patrick, very much for that and for that fascinating detail. Do we have a question that we can fetch for Patrick?
We do. It's really hard. We've got some really great questions, but this looks like a good one. And so Darian asks, how do you measure how tightly wound a galaxy spiral arms are when the galaxy is oblique to Earth's perspective?
Right. Yeah. So the issue is we have to weed out those galaxies that are completely edge on. So there's a certain inclination range that's actually useful. So obviously, if it's completely edge on, you can't see the spiral structure at all. But if it's at some modest angle, we can do some math, right? So basically, we can essentially rotate the image and stretch it out so that way it's circular, so that way it looks like it's face on, and then what we do is we show that artificially deprojected image to the volunteers and have them trace out the galaxy. And so we try to make all the galaxies look the same. We try to make them all look like they're face on, even though obviously not every galaxy can be face on, but we try to make them all look face on, so that way we have kind of a standard way of showing galaxies to the volunteers.
Fantastic. Thank you so much, Patrick, for that. And let's go quickly because we want to have some good Q&A time. here to an old friend of Astronomy Magazine, Sten Odenwald. There was a time when you would mention smartphone astrophotography, astroimaging with a smartphone, not terribly long ago, and it would produce some rolling of the eyes from most people in astronomy. But that has changed dramatically with the capabilities of these phones. And the guy who's literally written the book on this is Sten Odenwald. And mastered it. And Sten is an astronomer at NASA's Goddard Space Flight Center as well. STEM resource development at the National Institute of Air and participates in many NASA programs in space science and math education. One of his most recent projects is the Smartphone Astrophotography program, which we'll hear about tonight, which encourages people to take photos of the moon, planets, and star clusters with their telescope and smartphone, and they can help measure light pollution as well while doing it. So get your phone charged up, find out how to do it. Let's listen to Sten, and you're going to give us the pertinent URLs as well, I hope, Sten.
Yep, that's right. Thank you, David. I consider my projects to be kind of the bookend to projects like Aurorasaurus and Spiral Graph, which are projects that are targeted on specific astronomical or geophysical concepts and objects. What I like to do, and what I've enjoyed doing since I was an amateur astronomer as a teenager, is taking all sky photographs using common equipment that I had available to me. And for the most part, as a teenager in the 1960s and early 70s, you had to go to flea markets to get yourself a single lens reflex camera for 15, 20 bucks, and then find yourself a tripod, and then you'd set that up in your backyard and take timed exposures of the night sky. Well, from suburban Oakland, California, that had its challenges because of light pollution. Things got a lot better once I got a car and could actually go camping in Yosemite and get into the high Sierras where there's no light pollution. So that was a lot of fun. But anyway, so what I'm interested in is sort of the change in our sky quality over long periods of time. Night sky light pollution is a project that I put together which looks at urban and rural light pollution in the sky. And with that program, you basically set your smartphone on a tripod and take a photograph of the sky and submit that to the project, which then is added to the archive and correlated with other light pollution indices that are available. Satellite Streak Watcher, if I can get my own program pronounced correctly, came up because it turns out that SpaceX is putting thousands of satellites in near Earth orbit. And if you look at the twilight sky or the early morning sky, an hour before sunrise or an hour after sunrise, you will see the streaks of these satellites going across your sky. And it's the strangest thing that you've ever seen in your life. In the 60s and the early days, when there wasn't a whole lot of commercialization of space yet, satellites were very rare phenomena to see in the sky. And so you could take wonderful deep sky photographs and not worry about getting streaks and these sorts of things going across your image. Today, that's almost impossible to do if you're trying to photograph objects around astronomical twilight, which is 45 minutes after sunset or 45 minutes before sunrise. You will see these satellites streaking across your field of view. So the Satellite Streak Watcher is all about archiving this and to show the degradation of our night sky over a period of time, starting now, because they're just now starting to put these satellites up. And so in 5 years, there'll be a gazillion of these satellites going across the sky. And so this would be an archive of images showing the degradation of the night sky, the early evening and early morning night sky, which has some sort of interest in terms of assessing the quality of our experience of the sky. There are many segments of society that value the night sky for religious and other purposes. So I thought it would be a good idea to keep track of just how rapidly we're losing this valuable natural resource. We talk about night sky light pollution and the loss of our night sky because of urban light. But even if you're in a completely dark site, you're going to have these streaks and artificial satellites and all kinds of things buzzing across your field of view, increasing over time. Now, smartphone astrophotography is sort of the third project in this triumvirate. Here, the idea is simply to take a photograph of the night sky using a smartphone or some other small camera that's easily available for most people, and just photograph objects in the sky, astronomical objects. You can do wide field photography, you can do star trail photography, you can do photography through binocular or through a small telescope. The idea is to sort of try out different camera systems and see just how well they perform in detecting and photographing in a nice way some of these astronomical objects. That includes total solar eclipses, of which people are fascinated by. It also includes Aurora. As Liz has mentioned, there's a lot of interest in photographing Aurora. And it turns out that smartphones are really quite capable of doing a respectable job of photographing those sorts of objects. There are also other things that you might not think about as being sort of astronomical objects in a sense. How many of you have seen a phenomena called a sundog, or halos of light surrounding the moon, or halos surrounding the sun from Arctic locations? These are also, well, they're called perihelia if it's involving the sun, the equivalent for the moon. I have not the faintest idea what that term is. Let's call it a lunar halo. You know, those are also fair game. So anything in the sky that you think is interesting that's related to your appreciation of the sky, the night sky, or other things is fair game for this activity. So far in these three projects, we have close to 1,000 people who have submitted close to 1,000 photographs of a variety of things, from star clusters seen through small telescopes with the smartphone, to wide field photographs that show legions of Starlink satellites marching across the sky. Now, the idea is to get a large enough archive of these things to show the variety of things that you could see in the sky, and in this case, photograph, as a way of assessing how this variety changes over time. Now, also with night sky light pollution, there are also activities that keep track of just how badly that is deteriorating. All of these things, all of these images are uploaded to a set of archives. I use a platform called anecdata.org. So the way that you would do this is that you would take a photograph with your smartphone, you would download it to your laptop, step 2. Step 3 is you would log on to anecdata.org and get yourself registered. Then you would select one of these 3 projects. In this case, Smartphone Astrophotography is a project. And so you would join the project, and then you would upload that image from your laptop to the project observation page. The observation page asks you for some fairly bare bones information. What is the object name and things like that. But it also captures the GPS location of your phone at the time the photo was taken. And also the photo itself, you can interrogate the photo image file and recover a lot of information about, for instance, the camera optics, the exposure setting that was used on the camera, the GPS coordinates and things like that. And so all of that information is then available in the gallery of photos. And in fact, if you're joining this smartphone astrophotography project, or satellite streak watcher, or night sky light pollution, you can actually download these images yourself, or you can open up the gallery and see all the other contributions by other people. The really cool thing is that all of this information is geotagged, and within the anecdata.org app, you can display the map that shows where all of these pictures have been taken and all these observations have been made around the world. And so one challenge is to find places where nobody has thought of taking photos and go there and go there on vacation. Set up your tripod in the middle of the Sahara Desert or the top of the Eiffel Tower. I don't care where, but have fun, be creative about it, and try to come up with some really interesting, well-framed and artsy photographs of astronomical objects. As David mentioned, I have written a book on smartphone astrophotography for NASA, and you can download it at the URL spacemath.gsfc.nasa.gov, or you can just simply Google space math at NASA, and it'll go to the main front page, and there you will find the PDF file that you can download. So that's about it. Have fun and enjoy the night sky while we still have it.
Was muted there, forgive me. Thank you, Sten. We had an unfortunate incident early on in our program here, and that is we lost Vivian to an ill-timed neighborhood power outage. So we'll hope next time that Vivian is back leading this parade onward. But I think, Brian, you've been helping to vet some questions.
Yeah, we have a good question here from Lori. Lori asks if folks can shoot the pic on their smartphone and then also upload without having to go through a PC.
Yeah, you can certainly do that. Well, it's actually more direct. So the idea is you would go to your app store and download anecdata.org, and then you would open up the Anecdata app, register, give yourself a username and a password, and then once you're through, you can select smartphone astrophotography and then click on make an observation, and it'll have a thing in there that says upload a photo, and then you just simply click on that. It goes to your photo archive on your smartphone and uploads the image. So yeah, that's a very direct way of doing it. But if you're using a Nikon or other kinds of cameras that are not smartphones, then the laptop method is the one you'd probably be using.
Excellent. Have we other questions for any of the three panelists who've presented to us so nicely tonight?
We do, and so we have a number of questions here, and so let's kind of go back to the beginning. So William asked that he lives at 41 degrees north latitude. He's only seen a live aurora once in his life. How far north does he have to go to see the real thing?
Yeah, that's a great question. Many people are interested at those latitudes. It's really tough unless you are in really dark sky places, and also you're watching the groups or the data or signed up for an alert to catch the, half an hour when maybe there's a little bit of aurora visible once every few years. But you can always go north or south under the auroral oval, the kind of everyday auroral oval, where it really doesn't take much of the continuously variable solar wind to be giving energy into the Earth's magnetic field and releasing it in the form of spectacular aurora all over the sky. Places you can go that are well situated under the auroral oval include Fairbanks, Alaska, Yellowknife, Canada, which is a small town, but you can get there by a normal plane, Iceland, and like Tromsø, Norway, and other places in Scandinavia as well. Those are your best bet. Don't go in the summer.
All right, well, we could stay with Liz here. And so Dave asked, he might have missed it, but what does Steve stand for?
strong thermal emission velocity enhancement. And I also heard there was a question of how did it get named? It got named by a citizen scientist who came up with kind of a placeholder name, kind of a funny name, based on a movie, a kids movie called Over the Hedge. And the characters see this hedge in their forest, and they're scared of it. And instead of being scared of it, they just call it Steve. So some of the citizen scientists we collaborate with all thought that was a great name, and it really stuck. And the scientists like it too, most of them.
All right, well, let's go over to Patrick. And so I'm going to kind of combine two questions, one from William and one from John. One is the latest on the cause of the spiral arms, and then the other is clues about the bars of galaxies getting formed. And so kind of about how the structures are formed both ways in the spiral galaxies.
Yeah, those are good questions. Those are active topics of research. So let me talk about the bars first. So bars in spiral galaxies are actually very common. They make up, when you look at spiral galaxies, most spiral galaxies are actually barred. So the real question is, why don't galaxies have bars? And so it's actually pretty easy to create a bar in a galaxy. You just need a small satellite galaxy at some point to kind of distort the, let's say, circular orbits that make up a spiral galaxy. You just need something to come by, tug on the orbits a little bit, kind of elongate them and offset them from each other. And then you can easily create the spiral structure, and bars kind of form out of that as well. So they're actually pretty common and actually pretty easy to form. So now how does spiral structure actually stay maintained? So the best explanation we have is there's something called density wave theory, which essentially means that you have, let's say, orbits of material, orbits of gas clouds, kind of moving through a disk, and then there are regions of high density. So basically, what will happen is these gas clouds will kind of bunch up in regions and collide with each other, form stars, ignite, and kind of light up those dense regions and show you that spiral structure. But somewhat recently, there's been another theory proposed as how to create and maintain spiral structure, and it's called Manifold Theory. And I think I'm not real up to date on that, but I think the idea is that essentially you have these three-dimensional kind of tube-like structures that kind of emanate from the bulge of a galaxy, and the stars and the material kind of move through those tube-like structures in kind of a chaotic fashion, but they're contained within those tube-like structures, those manifolds. And so there's actually some evidence for it. There's evidence against it as well. So there's a little bit of a competition there, but I think still most people kind of agree that it's density wave theory, and a lot of the work that I've done kind of upholds that the density wave theory as opposed to the manifold theory for arm structure.
All right.
Excellent. I think we're beginning to run low on time. Maybe we do one more question, Brian, if you have one more good one.
Yeah, let's go one more question, and we'll go back to Sten for this one. Darian asked, is the new iPhone 12 night sky photography capability significantly better than Android phones? And are there any recommended astrophotography apps that work well for a smartphone for doing astrophotography?
Extremely good questions. Any of the recent vintage smartphones all perform comparably. They all use basically the same kind of imager sensor technology, and you'll be very satisfied with the faint light level photography you can do with all of these. They typically have apps that allow you to take images and stack them. Stacking is an important way of enhancing the sensitivity of astronomical images. Modern day smartphones, the ones in the last few years that have come out, have the stacking ability as a standard app feature for their low light level photography. So all you do is get your camera on a tripod, point it at the sky, tap the app, start it up, and it'll automatically take the requisite number of images to get right down to 6th, 7th, and 8th magnitude stars. That's why you get these beautiful pictures of the Milky Way that you see over and over again taken with smartphones. And you should see that kind of performance in all of the recent models at this point.
Fantastic. Thank you, Sten. And thanks to everyone. We have filled our hour. And it was fantastic. We learned a great deal from all of you tonight. It was very entertaining, and there's a lot of opportunity to get involved with these things and to really help push science forward in a very exciting era. So thank you, Liz. Thank you, Patrick. Thank you, Sten. Thank you, Vivian. Thank you, Darlene. Thank you, Brian. Thanks to everyone. It's been a great joy. I hope you enjoyed watching it, and go to these websites and follow up on the projects. There's a great deal of fun to be had, as well as real science here. So thanks to everyone so much. We'll sign off for tonight and hope to talk to you all again very soon.
And before we go, I want to remind everyone, we do have 2 more webinars coming up. Well, actually, we have several in the pipeline, but one of which you'll be particularly interested in. Next month, before we get to that one, on May 20th, we will have Dr. Casey Hannibal, who is going to bring us up to date on the Artemis program. And on June 22, we're going to have Dr. Carl Badams, who's going to give us this is a great title. I love it. Supersonic Snowballs in Hell: The Science of Sun-Grazing Comets, and about how you can help with a citizen science project looking at sun-grazing comets. And so that's definitely related to what we did this evening. So I love that title.
That's great stuff to look forward to. Thanks so much to.
So thank you, everyone. This will show up on the Night Sky Network YouTube page, as well as the Night Sky Network webpage by tomorrow. So thank you very much, everyone. David, thank you very much. Panelists, thank you very much for joining us. This has been a delight. And Vivian's out there in Cyberland someplace in a without electricity. So maybe she's not with us anymore. So.
She'll be back next time, though. Yeah.
She will. She will. So thank you, David. Thank you, Elizabeth. Thank you, Patrick, Donna, Megan, everyone. Darlene, thank you.
Thanks so much, everyone. Have a wonderful night, and follow up and help us push science forward.